Let's begin our afternoon session. So in the afternoon session, I will finish up the introduction to DNC, and I will introduce two applications of memory networks. So as I said, DNC was published in 2006 in Nature. And let me quickly remind main difference between NTM and DNC. So as it says, it extends NTM with advanced addressing mechanism. So the other backbone is identical, but in NTM, there were two addressing mechanism, but here they still use content addressing, but they also introduced two novel features. As a result, location addressing is changed to temporal addressing. So this is a visualization of DNC architecture. As I said, these parts are identical to NTM. But there are two novel information. The first one is usage vector. So here, wider regions show more usage. Therefore, when you write new information, you select slots that are used least. And the next one is temporal link matrix. It records the information which memory slots are used one another. So I will give the details in following slides. One important remark is that although these two papers are written by the same authors, but they use different notation. So you have to be careful with some changed notation. But I will explain one by one. So NTM, here's the output. Here's the output that controller should generate. But collectively, they are denoted by psi, and then I will explain one by one. So the first, this set of parameters are the same with the NTM, and these parameters are novel for DCM. In NTM, I just said there are multiple read and write heads, right? But here, they specify all number of read heads and a single write head. So here, they use superscript R. R indicates read head, and W indicates write head. So there are R number of read keys and one write keys. Also, there are R number of strengths and a single write strengths. And there's a erase vector, and there also a write vector. But here we use head notation for erase vector. And finally, the erase vector is obtained by applying softmax on ET, sigmoid on E hat T. So here, ET is obtained by sigmoid on E hat T. And now I will introduce the new novel parameters. First, there are all free gates, so I will explain later. And FTI is obtained by applying sigmoid on F hat, and G denotes allocation gate. I will also explain later, and write gate and R read modes. So all of them will be discussed in following slides. So as you can see, the main difference from NTM is that DNC includes more weights, and they have many scalar gates to interpolate among weights. Actually, they are denoted by vectors, but usually each of them is 3 by 1 vector. So as a result, they are also scalar gates. So now I will explain the two key ideas of DNC one by one. I will first explain dynamic memory allocation. For this, we use UCG vector, and later I will explain temporal memory linkage. So the objective of dynamic memory allocation is that we let the controller to free or allocate memory as it needs. So in order to do that, the idea is keep tracking memory usage vector, UT, and N indicates number of memory slots. So UT is going to be N by 1 vector. And this value, the range of UT is from 0 to 1, and it's going to be a continuous value. The intuition is that we allocate the memory for writing with a low UT. So low UT value. So here's a memory slot, and we define a UT. And if this memory slot has the lowest UT value, then we use this slot for writing new information. So that's the key idea. So yeah, dynamic allocation can be achieved by keep updating usage vector UT. So now I will explain how to compute UT. So it's pretty complicated. So initially, you initialize U0 to 0 vector, N by 1 0 vector. And then you keep update UT from UT minus 1 using this equation. So suppose that this visualize previous step usage vector, and suppose that this is a write weight in previous step. So the idea is that you first add these two terms. If this value of the first slot is large, then UT is large. Why? W parameter indicates how the proportion on the memory slot for writing, right? This is a weight for writing head, and if this value is high, it means that at time t minus 1 step, the first slot is used for writing. Therefore, at previous stage, the first slot is used, write it. Therefore, its usage vector should be increased, right? So the current usage vector is based on previous usage vector. But if some slots has a high W value for writing, then its usage vector value should be large. It means that this slot will not be freed for new information, right? Because at previous step, it is used for writing. So you should increase the usage vector for that slot. Any question about this? And then you perform dot product, ut minus 1, and this value. You perform dot product between these two vectors, and this is the output of dot product. Center dot indicates point-wise multiplication. So it means that ut minus 1, it means the point-wise multiplication between ut minus 1 and right weight rate at previous stage. And then here they introduce psi for the value. So psi is called memory retention vector. So its size is also n by 1 vector, but its value is from 0 to 1. So it indicates how much each location will not be freed by the free gate. So psi t is computed by this equation. So R is the number of read rate, read heads, and it is defined like this equation. So the basic idea is that given a memory slot, if this memory slot is right, was written in previous step, then its ut value should be increased. But in previous step, this slot is red, then its usage value decreases, right? So for this memory slot, at previous step, if controller write the information here, then U value should be enlarged. At the same time, at the previous step, if this slot is read by controller, then its usage vector is decreased, right? So if some slot is already read, it means that it's likely to be important in later. But in previous step is written, then it's likely to be used sometime in the future, right? So this is a basic idea. UTI, I slot usage vector value is increased after each write. UTI is decreased after each read, but it's proportional by free gate. So any question about this idea? So in order to implement these two ideas, they come up with this equation. Actually, this slide is the most important to understand usage vector. So this is a two principle about how to update UT value. UTI is increased after each write. So at previous time step, if I is written with a high value of weight, then UTI should be increased. But in previous step, it was read by head, then UT value is decreased. And there are R number of heads, therefore we use these product values. So some particular memory slot was read by many different heads, then its value will be lower. So that's the key idea. But the weight of how much we decrease the value of usage vector is controlled by FT. And this FT is generated by controller. So that's the basic idea of how to update UT. So anyway, the important thing is this. So you may not completely memorize or understand the equation, but these two principles are the most important to how to update UT. And these two principles are implemented by this equation. So once you understand these two, then you can easily derive those two equations, satisfy these two principles. And then, yes, there are so many notations and symbols, so it's a little bit complicated to understand. But anyway, so there's a new vector, pi t. Its size is n by 1 vector, but its value is a positive natural number. So simply speaking, pi t is simply sort the memory location in ascending order of UT. So for example, UT is 4-dimensional vector, and suppose that this is 0.1, 0.3, 0.4, and 0.05, then pi t1 is going to be 4, pi t2 is going to be 1, and so on. So pi is simply sorting of the memory index in ascending order of UT. And then now we are going to compute allocation weighting, AT. And AT is denoted by delta n. So delta is newly introduced in the paper. So it means that n by 1 vector whose values are weighting. So it means that delta n, delta small n means r n by 1 with every single value is larger than or equals to 1, and its summation is to 1. So this is an n-dimensional weight. So delta n indicates n-dimensional weight. So summation of AT should be 1. Every single AT should be larger than or equals to 1, 0. And its dimension is A. So the paper introduced this notation for that. So AT indicates allocation weighting. So its key idea is that if UT value is large, suppose that UT value is large, then AT value decreases, right? It means that if usage value is high, then we should not allocate for new information, right? Therefore, AT value should be low. So if one slot has higher value of UT, then its AT value should be low. So AT indicates the waiting for data allocation. So this equation, so theta t is already sorted in ascending order. So it means that this equation means that we simply compute, multiply the previous ranked UT values for each I. So for each J. So that's a little bit complicated, but you see what I mean, right? So we compute UT and we sort UT according to its value in ascending order. That's going to be pi t. And once you have pi t and UT, you compute AT. So AT is going to be used to decide which memory slot will be released or allocated. So any question about these equations? And then now I will explain how to use AT later. And then now we move to the second feature, temporal memory linkage. So this is the second feature of DNC. And the objective of the second idea is keep track of consecutively modified memory location. So for that purpose, they design linkage matrix, LT, which is n by n dimensional matrix at time t. So LTIJ indicates the degree to which location I was the location written to after the location j. So it's very complicated. But suppose, let's consider with an example. Suppose that LT is look like this. So if you find non-zero element, then 4, 1 is 1, 1, 2 is 1, and 3, 4 is 1. It means that according to this definition, 1 was written, then 4 was written. 1 was written, after that 4 was written, because LTIJ indicates the degree to which location I was the location written to after location j. So it means that this indicates 1 was written, after that 4 was written. So from the second one, we can know that 2 was written after 1, and then 1 was written. And the third, from this information, we can know that 4 was written, then 3 was written. So if we collect or consider all information, then we can recover order of writing. So 1 was written and 4 was written. So we know that 1 to 4, and from 2 to 1, and then from third argument, 4 was written, and then 3 was written. So simply speaking, LT indicates the order of writing to memory slot. Any question about this? So LT. So the idea is that DNC keep track of this LT. So if you have a LT, then you know that in what order the memory slot was written, right? But the important thing is that in practice, every single value are going to be continuous value from 0 to 1. Because, as I said, we are not going to use discrete or binary values to guarantee differentiability, right? So in practice, so this is an example to explain LT. But in practice, every single value in this matrix is going to be a continuous value from 0 to 1. So any question about this? Yes? Huh? How to determine LT?
How to determine the entry point? I mean, in this case, it is 2. Which one is the first location?
From this information, we can reconstruct this order, right?
But how do I know 2 is the first?
Because 1 was 1, then 4. There's a 1, then 4. And from the second argument, 2, then 1. So 2, then 1. And
okay,
then from third argument, 4, then 3. So as a result, we get this information.
I see.
And what if we had a fourth line there saying that first 3 was written and then 2? if we had another fourth line saying that first 3 was written, then 2 was written, then it forms a loop. There is
So
no
yeah,
beginning,
there will
no
be a
end.
loop. There will be a loop, but unless, so actually they are going to be a continuous value. So some, the latest information will have a higher value. So in practice, yeah, there will be a loop for writing, but all the information will be decay again and again. So yeah, this is an example to explain what information LT includes, but in practice, they use continuous value or wait to update this value. So now I will explain how we can compute LT values in practice. Yeah, as I said, LTIJ is not binary, but continuous because we want to guarantee this differentiability, right? So here's, we describe how to compute LT, how we can compute the LT. So for the purpose, we first define PTI, the degree to which location I was the last one with written. So WT is the writing weight at time step t, right? So it means that this is an n by 1 vector, but if this value is largest, it means that at time step t, the first slot is used for writing, right? So this W has the information which slots are written at previous time step. And then it means that if some slot has a higher WT value, then its PT value should be also high, because PTI indicates the degree to which location I was the last one written to, right? So you keep update PT in this way. And then once you compute PT, then you compute LT I, J in this formulation. So it means that this is a previous L value. And previous L value ignored if WT is high. It means that if a previous step, that particular location is written, then LT value for that position is decreased, right? And then we simply compute WT and PTI as a result. This is high when I is written at time t, and J is at t minus 1. J is at t minus 1. So in previous step, J is written, and current step, if I is written, then Lij has a high value. So simply speaking, the first term is about forgetting. How we forget about previous L values. And the second term tells the definition of L. So at previous t minus 1 step, J is written. And at current step t, if I is written, then this value will be high. Therefore, LTIJ will have a high value. And in this particular example, if at current time step, I is written and J is written, then this value will be high. Therefore, for IJ, we ignore previous value. So again, so all equation is a kind of weighted summation between previous information and current information. And the weight are controlled by gate value. So gate value. So that's the big idea of this. And then once you compute LT, then we can compute F and B. B is called backward weighting, and FT is called forward weighting. And both of them is n by 1 dimensional vector whose values are larger than or equals to 0, and its summation is 1. So basically, BT and FT indicates the degree to which location J was written before and after the last read location. So if you look at this equation, this part is the same, and you use LT or transpose LT. So it means that it's just to say forward and backward. So roughly speaking, both of them has the more or less similar information, but this is about backward and this is about forward. By you simply transpose LT matrix, right? Okay, so let's take a look at this, and I will explain this gate later. So anyway, I just finished explaining about two new features, and then now we move to how we can compute read and write weighting. So for the write weighting, we use content-based addressing and dynamic memory allocation. So dynamic memory allocation is about write, and temporal memory linkage is for read weighting. But for both cases, content-based addressings are the basic. So for the content-based addressing, they use different notation, but the idea is exactly the same. We already seen beta T, and this is a key, and this is a memory slot. The memory content as slot I. So you can compute, you can first compute the cosine similarity, which is multiplied by strength and apply softmax. So that's going to be represented by this notation. So now I will explain write weighting. So write weighting means WTW. So this is a combination of content-based addressing and dynamic memory allocation. So CTW is a content-based addressing. So content-based addressing is denoted by CT. And here's the AT. What is AT? We compute AT here. Allocation weighting here. So we use that value to compute AT. So there's a gate to control how much we use the information from AT or from CT. So there's a gate, and there's another gate. So this is called the allocation gate, and this is a write gate. So yeah, those two parameters are the output from controller. So on allocation gate, you interpolate between writing to a newly located AT location or existing one founded by content equation. So based on content addressing, we find out the most relevant slot by the content addressing, At the same time, we use 80. It means that this is relevant. At the same time, this usage vector is small. Then we first write the new information here. And therefore, writing weight for that location should be large. So this is a content-based addressing, and this part is about dynamic memory allocation. As a result, you get WTW. So that's a right weighting for at time step t. And this is about read weighting. It's WTR, 1. So as I said, there are big R number of read heads. So we use the superscript small r. So likewise, it uses content-based addressing and temporal memory linkage. So in previous step, we compute F and B, right? F and B. And C is computed from content-based addressing. So this is this value comes from content-based addressing, and these two values from temporal memory linkages. And pi indicates the weighting between them. So I simply remind what the B and F means, and C means the content addressing value, and pi ti is a three-way gauge, interpolates among iterating forward, backward reading by content. So once you compute WTW and WTR, then writing and reading vector are the same. So reading and write are the same as NTM. Once you compute WTW or WTR, then you can simply update memory in this way, and you get the read vector in this way. And both the equations are the same with neural Turing machine. So anyway, so in summary, memory update and reading are the same. But the only difference is that when we compute W, we consider dynamic memory allocation and temporal linkage when we compute W. So in previous neural Turing machine, when we compute W, we don't consider such information. So this is the end of DNC. So does anyone have any questions? So it's pretty complicated, but if you closely look at this slide one by one, then you will see how it works. If you read the papers, actually this is a Nature paper, so main draft has no information about this. So you have to look at supplementary, but supplementary is pretty long, but they simply mention one or two sentences to describe the meaning of each equation. So it's a little bit hard to completely understand those computations by simply reading the papers. But the important thing is you can simulate by increasing any value or decreasing any value, then you can understand how different values are interconnected with one another. So, okay, so if you don't have any questions, I will move to experiments. So, as I said, this algorithm is pretty general to solve many algorithmic tasks. So in this paper, they apply DNC to solve graph tasks because, as you know, RNNs are very good at processing sequence information, but RNN cannot handle with graph structured data. So in order to show the generality of this method, the authors apply this algorithm to graph structured data. So they solve 3 different tasks, 3 kinds of queries on the 2 specific graphs. They consider 3 tasks of transversal, shortest path, and inference. So I will give an example in the next slide. And they also consider 2 different types of graphs. The first graph is London underground map. So they also consider family trees. So it means that Ian and Jody get married, and they have 3 children, 2 daughters, and 1 son. So rectangles indicate male, and circles indicate female. So they solve these 3 tasks for these 2 types of graphs. So actually, graph structures are organized like that. So there are a set of triples, 2 nodes, and the edge label. So it means that in underground example, Oxford Circus and Tottenham is connected by central line. And Tottenham and Oxford Circus is also connected by central line. Baker Street, Marylebone is connected by circle line, and so on. So you can represent London underground map using these tuples. So in family tree, they also represented by 3 tuples. Charlotte's father is Alan. Simon's father is Steve. Steve's first son is Simon. Nina's mother, Allison, and so on. So the thing is that these graphs and this graph and this graph can be represented by a sequence of 3 tuples. 3 tuples, right? So graph structures are like this. And then now I will explain the 2 tasks. So here's a test example. So the first task is traversal question. So simply speaking, it's a kind of a fill in the blank question task. So you are given this kind of blank tuples, 3 tuples with blanks, and your answer is to find out the correct answer for each blank. So that is called traversal task. And the shortest path question is that you are given 2 destinations, and your answer is a sequence of 3 tuples to get the destination with shortest path. And then the final inference question is that what is the Freya's maternal great uncle? So you find Fergus. Yeah, it's pretty complicated, but maternal great uncle. So yeah, so in summary, they use these 2 types of graph structures and solve these 3 tasks. And here is an example of one result. So this is a question of traversal. So these are the input. These are the input of network structure. So these are the input of network structure. And here's the query for traversal task. So our goal is to find the correct answer for the blanks. So that's the goal of the task of traversal. So in this particular example, given the first input, as you can see, green rectangle indicates right, and red and blue rectangle indicates read. So this part is graph definition, and this part is query. So given every single graph definition, the DNC write this information to every memory slot. And then they are given query. So for the query, DNC should write the query information like that. But at the same time, they read the relevant information. So the first information, Victoria, blank Victoria N. But the fourth context has a Victoria. Therefore, the first read head access this information. At the same time, they write the information of a query. And after answer this question, they not only read the query, at the same time, they access the graph definition that are relevant to answer the query. So they visualize the W. So it means that, roughly speaking, this is a WT, right? And this indicates WTR1, and this is a WTR2. So these values are visualized. So it means that this value is large at this time step for this memory location. So
why are there two visits to Oxford Circus, Tottenham Court Road? Because in the answer that one appeared twice.
Which one? Which one?
The first one,
Yep.
Oxford Circus to Tottenham Court Road.
Yep.
If you see under answer, if you go to answer, yeah, that one.
Yep.
And then the answer, it's included twice. Answer column behind your head, to the right of your head, if you look up,
Yep.
to the right, you
Yep.
see there's two squares.
Yep.
Does that mean that one should visit that place twice? But that makes no sense.
Could you point out? Could you come here and point out?
At the top,
Ah,
just
okay.
under the word answer, you
Yep.
see it's twice, the
Yep.
same line is traversed twice.
Yep.
Why is that?
One, two, three. 1, 2, 3. 1, 2, 3. You mean this is not centrally?
No, but if there's the read, if that's twice for that one, doesn't it mean that you
Yeah.
will pass through it twice?
It means that when you answer the first question, you read it, and for the last query, you also read it.
Okay.
So to answer this, to answer the sixth query, you have to read the question. You also have to read graph definition. Oh, for these two. So yeah, as you can see, the first read head, read the question, and the second read head focus on graph definition to answer this transversal problem. And right head is used to write graph definition and also in query definition. And then when you answer, you have to read query. At the same time, you also need to access any graph definition information. An important thing is that, as I said, this visualize delta t, right? W, and this indicates WT. R1, blue indicates WT. 2, read 2. So anyway, the computation of W is the most important operation in this DNC algorithm. So this is the conclusion of memory network model. So memory networks are a class of a model that combine large memory with neural networks that can read and write it. To fulfill complex tasks, we need to combine knowledge and reasoning. So yeah, these are the summary of the memory network. And I summarize some major challenges. So the first challenge is how to represent the information stored in the image. So what types of information we have to use. And sometimes the information may have some hierarchical information between different inputs. Then we may need to use a hierarchical memory structure instead of a flat memory structure they used. And the second major challenge is how to organize the memory if the memory is very large. So modular network is another very promising direction. So there are several papers about neural modular networks. And the final one is this is relevant to scalability or online learning. So if you apply your memory network algorithm to online learning, then memory should be lifelong learned. So there are several key future questions. Or if you have good applications where memory networks help a lot, then yeah, you can also study about them. So any question about what I covered until now? So DNC is a little bit complicated, but important thing is every single equation is simple. The complexity comes from too many symbols. There are too many symbols, but every single equation is not so complicated. So you can simply draw vector, n by 1 vector, and then you check whether if this value is large and what if this is value large, and so on. Then what if the LT is changed and so on. So you can understand each equation from those simple simulations. But there are 2 parameters. I agree. Yeah. So if you don't have a question, then I will explain some interesting applications where memory networks are applied. So I will introduce two papers, but I have only 30 minutes, so I focus on high-level idea. So the first paper I'd like to introduce is the application of a memory network for summarization of informal online text. Actually, this is submitted to this year EMNLP, but scores are not bad, so I think yeah, it's likely to be accepted. So yeah, the decision will be out in 1 week. Anyway, so I will introduce the application of a memory network for text summarization. So as you know, the goal of text summarization is to produce an abridged version of a text that contains information that is important. So source document is pretty long, consists of many sentences, and what we expect is to generate a single sentence that captures the most important part of the input document. So that's the task of text summarization. And broadly speaking, there are two different approaches to solve text summarization. The first one is extractive summarization. It means that, as its name says, it performs summarization by extracting sentence or words from the source text. So it means that you try to find out which words or phrase or sentences should be retrieved to generate the sentence. So you form summary by copying parts of the input. Abstract summarization is a little bit more challenging because you have to generate words or rephrase not featured in the input. So you may first understand the document, and sometimes you may need to use different words with the same meaning. So yeah, as you can easily expect, abstractive summarization is more difficult. So there are many summarization benchmark data set, but we first analyze existing data set, whether they are good for abstractive summarization. So here, this is a result from this paper, ACR 2017 paper, and it means that even simple extractive method outperforms the state-of-the-art abstractive method. So these are the abstractive methods. And these are the simple extractive method. Read-3 baseline is that you can just retrieve first 3 sentences as a summarization. So it's very naive approach. You can just retrieve the first 3 sentences. But it turned out that this simple and dummy baseline works better than state-of-the-art abstractive methods. So we take a look at why this happened. So why does this happen? So we realized that there is some bias. There is some bias in existing summarization data set because most data set originated from formal documents. So there are many data sets for summarization evaluation, but most data set are based on the text from formal documents, such as news or journals. So this slide shows that there is a location bias. I mean, in this kind of formal documents, always the most important information exists at the beginning of the document. So you can simply retrieve the first sentences. They are likely to be good summarization because most existing data sets are based on formal documents. So when you write formal documents like a paper or news articles, you are taught to write the most important sentence at the beginning of document. So this is visualize the location bias. So for example, this is a CNN Daily Mail data set. So in CNN Daily Mail data set, we have a pair of source text and reference summary. And we search for where reference summary exists in the document. But it turned out that at the beginning, most of reference summary exists. So we measure this Ngram model, but high-level idea is that CNN Daily Mail data set or newsroom data set, both of them are based on news articles. Therefore, reference summaries are likely to occur at the beginning of documents. So that's our assumption that even simple extractive methods outperform state-of-the-art abstractive model. So our argument is that the data set has some problem. The current data set has some problem because it has very high bias because they are originated from formal documents. So our solution is that we introduce a new data set and we define two desired characteristics for abstract full summarization data set. So source text should not follow strict formatting, unlike news article or journal. And data should be created by diverse users to avoid writing style biases. So in order to that, we generate new summarization data set called Reddit TIFF data set. So actually, the data set is collected from one subreddit, and specifically TIFF subreddit, because TIFF subreddit has very strict rule. So they have very strict rule for the post. So rule 3 is that title must encapsulate the post, and all posts must end with TDDR summary. Otherwise, that post will be removed or deleted. So in next slide, I show an example of post of TIFF subreddit. So actually, this Reddit is a kind of diary, daily journal. So authors write an interesting story in his or her daily life, and then title should encapsulate the entire post. Otherwise, it will be deleted. At the same time, at the final, the author should write TDDR as a summary of this document. Therefore, we crawl all TIFF subreddit, and we consider this body text as a source text, and this is a short summary, and this is a long summary. And the algorithm should generate short and long summary from this document. So this is the statistics of our Reddit TIFF data set. This is collected from subreddit TIFF, and it consists of 120K source text and summary pairs. Yeah, we do some post-processing. And this measures novel n-gram ratio. So this is a total n-gram in reference summary, and this is the n-grams in the reference summary that do not appear in source text. So as you can see, novel n-gram ratio is pretty high compared to existing data set when we use 1 gram, 2 gram, 3 gram, and 4 gram. So it means that reference summary contains novel n-gram that do not appear in the source text. It means that if that rate is high, then data set is more abstractive. And this is the visualization of locational bias. And this is a newsroom data set. But as you can see, our data set shows a uniform location of reference summary in the text. So one contribution is develop, collect a new abstractive data set. And the second approach is that second contribution is to design a novel summarization method for abstractive summarization. But the previous models is previous model is based on seq-to-seq model. Seq-to-seq model is very popular for machine translation. So basically, it's a RNN-based model. And based on seq-to-seq model, there are many variations. How to use attention. So by given attention, they can summarize the text. So they integrate seq-to-seq model, VAE, or point generator, and so on. But our argument is that previous approach suffer from two problems. The first problem is they are basically RNN-based method. Therefore, it suffers from vanishing gradient. If source document is very long, then RNN's hidden stage may not be good enough to summarize the whole text. And another thing is that the second problem is also relevant to what we already discussed. So source test is input one by one, and all of them are connected by hidden stage. But as you can easily expect, many of source texts are not important for summarization. Therefore, that could be another issue. So in this work, we proposed a multi-level memory network model, and we realized that this is the first memory network model for text summarization. So in previous research of text summarization, no one has used memory network, but we'd like to argue that summarization requires very long input. Therefore, memory network should be good for this purpose. And by using memory network, we can alleviate the two problems. So memory network can capture long-term information explicitly. For the second problem, we can ignore unimportant information, and we also use convolution operation to generate memory input. So I will show you one by one. So this is a visualization of our approach, our model. So specifically, there are 4 novel features. So when we write the information in each memory slot, suppose that there is input sentences, and then we perform convolution, and then the first convoluted output is input to the first slot, And then we use multi-level memory network. Therefore, we also apply convolution in next level. And this information is input to the second level memory network. So it means that we have multi-level memory networks, and the content of each level memory networks is obtained by different convolution with different receptive field. Therefore, in low-level memory networks contain the information with small receptive field, but high-level memory network will have much large range of receptive field information. So I will skip the details of the experiment, the models, and then I will show you the experiments. So the idea is that our method shows much better perplexity values. For the perplexity, lower is better, and in terms of Luge scores, our approach was the better in previous approach. And in our data set, abstractive methods significantly outperforms. So it means that our data set is abstractful, as I argue. And we also perform user studies via Amazon Mechanical Turk. It means that given a source text, we show two summarization results. One is by our method, the other one is another method. And we shuffle the order of summarization and ask the talker to select which one is better. And as you can see, our approach consistently show better votes compared to seek-to-seek attention model, DRGD model, SEASS, and PG model. So all of them are abstractive summarization methods. So here's an example, summarization example. So given this source text, this is a ground truth and our prediction and baselines prediction and so on. So anyway, this is a kind of paper that widen the applicability of our memory networks. So I think there are many tasks where memory networks can be very good. So this is one example. And now I will explain the memory GAN paper. So this paper was published in iClear this year, and the source code is available in GitHub site. And the title is this. I guess many of you already know about GANs. GANs are generative model. So GANs are used for generate or synthesize new image. So that's one particular example. But our idea is that in order to generate well, memorization is important. So our goal is to learn unsupervised GANs with memory networks. So there are two issues of unsupervised GAN. So I will very, very quickly remind you the GAN framework. So GAN consists of two components, generator and discriminator. And generator takes a noise input. Usually that is sampled from Gaussian distribution. And then they generate example, like an image. And suppose that there's a real image. And the discriminator is trained to learn, is trained to decide if fake is given, then its output should be 0. If real image is input, then it should be predicted with 1. So that's the basic idea. But there are two issues that almost all unsupervised GANs suffer from. So no matter what GAN models you use, these two problems always exist. The first one is generator suffers from structural discontinuity, and discriminator suffer from forgetting. So I will explain the details of these two problems. So the first problem is structural discontinuity. So it means that GAN, the generator, use Gaussian distribution to get input noise. And suppose that you apply GAN to CIFAR10 dataset. As you know, CIFAR10 consists of 10 different classes, right? So if we learn generator on this dataset, it means that you embed 10 different classes into a single unimodal continuous Gaussian distribution. So it means that generator takes an input from a Gaussian distribution, and if the noise comes from here, then it generates a human. But if random noise comes from here, then it generates a dog, and so on. So it means that if you finish learning generator, then it implicitly embed 10 different classes into a single unimodal distribution. So if you learn in this way, then suppose that this area is for penguin and this area is for Siberian husky, for example, but this is a continuous space. Therefore, if you sample from here, then it's going to be general. It may generate the class that does not exist in training data set. So that is unavoidable. So this is a fundamental issue when you use single continuous distribution for discrete classes. So in another way, we do not know a best latent modality within a data of priority. So in next slide, it shows an example. So we train DCGAN for MNIST data set. So DCGAN uses a single Gaussian distribution, and DCGAN consists of 10 different classes from 0 to 9 that are written by different persons. So there are style variation. So once we train DCGAN, and we randomly sample 4 different Z, and we randomly sample 4 different Z, and the first Z generate this, and the second Z generate this, and third one generate this, and fourth Z generate this. Once we do that, we interpolate between these 4 Z with 64 different points. So, and then from those Z, we generate image. But as you can see, there are some images that are not any number. So you cannot avoid such problems. So we observe the similar problems in fashion MNIST. And let's take a look at the second problem. Second problem is forgetting issue. So as you know, GAN training is notoriously difficult. The main reason is that when you train GAN models, you have to consider dynamics. So as you know, discriminator should be trained slightly better than generator. Otherwise, if discriminator is so good, so if it completely correctly classify any generate image from generator, then we cannot train at all. So what we expect is that from beginning, discriminator should be slightly better than generator, and both of them should be better and better again and again. So that's one reason why GAN training is difficult. But discriminator suffer from catastrophic forgetting. So this is very common problem for any online learning algorithm. Its basic idea is that initially discriminator can successfully classify this faked image, but after long time, the parameters of discriminators are changed. So suddenly it cannot correctly classify previously correctly classified image. So it means that it catastrophic forget the previous examples. So that's unavoidable for any kind of online learning algorithms. So here are two solutions to resolve these two issues. The first idea is that discriminator parameters are keep updating, but you add regularizers between new parameters and old parameters. By doing that, when you update discriminator parameters, you have to memorize the old parameters by adding this regularizer. So, but this is pretty naive approach. And then the second idea in previous paper is that they use a buffer of synthesized image. So it means that at time t, so there is a buffer. So you add faked image, old faked image in the buffer. At time step t, generator generates new faked image, and then you also take some of buffer images and then use all of them as a fake image at time step t, and let the discriminator correctly classify all of them. So this is another naive approach, right? So you simply set a buffer for previously synthesized images, and later you just give those examples to the discriminator not to forget about them. So that's another issue, another idea. But our idea is that both problems can be mitigated by using lifelong memory network. And okay, so I will explain how memory GAN can bypass these two problems. The first problem was structural discontinuity problems, and that is caused by embedding discrete classes into a continuous distribution. Therefore, we add memory, and memory memorizes the information of a class. So simply speaking, we split modeling of class and style. So style is learned by Z, and class information is learned by memory network. It means that we separate learning of class and style. By doing that, we do not suffer from structural discontinuity problems. And the second issue is that discriminator suffers from forgetting problem, but now we have an explicit memory. Therefore, it's quite obvious that we can avoid forgetting problem. So that's the two key ideas of our paper. And I will only explain overview of memory networks. So usually this is a generator, and generator takes random noise Z and generate fake example. And this is a discriminator. Discriminator takes this image and then compute this value. The probability that X is real. Probability that X is real. But in our model, we add memory network here. So discriminator takes not only random noise and key value. So key value indicates which class will be generated. So now generator has two inputs, and then they generate fake samples. And now the discriminator, in original discriminator directly compute this here. But in our model, discriminator generate a vector mu, and this is a query, and there's a key values, and we perform marginalization of a memory network, and then compute probability that X is real. So anyway, so I may not have time to discuss about the model detail, but I will show some experimental result. The first one is quantitative result, and actually measuring the quality of synthesized image is very difficult. But people, previous work devise inception score. So this is a kind of implicit measure of quality of image, and our model achieved the best inception score on CIFAR-10 as of iClear submission. But in iClear 2018, there were other papers that report the better score. But anyway, so at the iClear submission, it was the best. And this is one qualitative example. So one of reviewers asked that we use memory network, so probably our model may memorize training data themselves and then generate training, simply retrieve training example to generate realistic image. So as a rebuttal, we show these examples, and it means that the leftmost examples are generated by our algorithm. And the next 10 images are nearest images in the training set. As you can see, the generated images are new compared to training image. So it is an example that our memory network, memory GAN, does not simply memorize training examples to generate synthesized image. So yeah, this is another qualitative result, and these are successful examples, and these are failure examples. So yeah, this is a very, very quick introduction to memory GAN paper. And so this is an example that where memorization capability is useful not only for RNN, but also for other neural network models. And if you have a question, please ask me. Okay, so then I will stop my presentation here, and you can ask during break time. And yeah, thank you for your attention.